Okay, to make sure that we stay on track, we will get started with the midterm 3 review. We'll have another one of these next Friday for part of the final exam, so we'll be back here exactly 1 week from now as well. Typical story for these exam reviews, if you've been to them before, you already know this, but you're welcome to interrupt me with questions anytime. If there's any topics you want me to go over in more detail. For a lot of the problems today, especially, I won't skip steps, but I might go through things quickly that I think are pretty self-explanatory, but if that's not the case, please stop me and I'd be happy to slow down on any of these. All right, so with that, we'll dive right in. So the first question here, as you recall, this exam question covers chapter 7, 8, 9, and the questions are roughly in order of those 3 chapters, and that'll be the case on your actual exam as well. So the first question deals with expansion work. So we want to calculate the work when a sample of N2O expands from 3.75 to 8.25 liters against a constant pressure of 957 torr. We only learned about one kind of work in this class. In physics, there's obviously a lot of other calculations you can do for work, but we only learned about the expansion of an ideal gas. And in this case, there's a pretty simple equation. Work is equal to the negative of the external pressure times delta V, which tells us that delta V is the change in volume. If the gas is expanding, the volume is getting bigger, the work is negative, and it's the opposite if you're compressing the gas. So that's really the only equation we need to worry about. The only thing we need to think about in these problems that's beyond this is the units that are involved. So we see that all of our answer choices here are in the units of liter atmospheres, which immediately tells us that we want our pressure term to be in atmospheres and our delta V to be in liters. And in some cases, we would have to also convert to joules, so we'll cover that in a second, how you would do that, but we don't need to do it here. We just need pressure in atmosphere and volume in liters. So we need to convert our external pressure that's given to us into atmospheres. So this, again, reviews some of the things from Chapter 8 as well about units of gas pressure. So our external pressure is 957 torr, and one of the 2 pressure conversion factors that you should be very familiar with for this test is that 1 atmosphere is equivalent to 760 torr. So that's going to get this pressure into the correct units of atmospheres that we need for this particular problem, 1.26 atmospheres. And then remember that delta V is equal to final minus initial. So anytime we see delta, that's what we want to think about. So we're expanding from 3.75 to 8.25, so that means the gas volume is getting larger. Final volume is 8.25, initial is 3.75, it should be positive delta V. So 8.25 liters minus 3.75, which is, I hope I did that right in my head, 4.50 liters, I believe. Yes, okay, good. And then finally, we're going to put these into this equation up here, which is a negative sign out front, the pressure in atmospheres, and then the delta V, which is 4.50 liters, the 2 volumes subtracted from each other. And what we end up with is minus 5.67 liter atmospheres. All right, this is already in the correct units again because our pressure is in atmospheres and our volume is in liters, so we set that up for ourselves already. So this is the number that we're looking for, and that corresponds to choice B. So especially in questions of this type about work, we should be able to know the sign right away from whether it's expansion or compression. Remember, expansion is negative work, compression is positive work, so we want to make sure that the answer we get in this case is a negative number because we're going from a smaller volume to a larger volume. Other than that, it just comes out to multiplying the numbers correctly. Also remember, in some cases, we'll want you to convert to joules. So 1 joule is 101.3 liter atmospheres. So you might, and I think often we'll give that conversion to you if you need it, so you don't have to memorize it. But if you don't memorize it, there's an easy way to remember it. So remember that we have 2 values of R on the periodic table. So this is a little trick I'll show you that you'll sometimes need if you're trying to remember that conversion. So we have our periodic table here, and we saw that there's 2 values of the universal gas constant R. There's the 0.0821 liter atmospheres one that we often use for ideal gases, as we'll see later today, and the one that we've seen more recently is 8.314 joules per mole K. So if we divide those 2 by each other, let's do it the other way. Yes, sorry, we'll get 8 point. I think did I screw that up already? Jeez. See, this is why if you don't remember it, do what I'm doing here. So 8.314 joules per mole Kelvin, which is the one value of R on our periodic table, divided by 0.0821 liter atmospheres per mole Kelvin, which is the other value of R. The moles and the Kelvin divide out, we get joules per liter atmosphere. I think I had it backwards. It should be 101.3 joules is 1 liter atmosphere. So if we wanted to convert this number to joules, you have to multiply by 101.3, which we're not going to do here, but if you had to, that would be what it is. So if you forget this conversion, which you're going to sometimes use in these problems, just divide the two values of R and you have it, so you don't have to necessarily memorize it. All right, any questions on this problem? All right, that was again a little bit of extraneous information, but hopefully it will be helpful for some of you on the test. And then the next question here, number 2, is dealing with change in internal energy. So change in internal energy is what we abbreviate as delta E, E being the internal energy of the system. And we want to know what is the change in kilojoules when a system absorbs 965 joules of heat and has 456 calories of work done on it. So in these types of problems, when we're calculating delta E, and especially when we're using heat and work to do that, it's again a very simple relationship. Delta E is equal to Q plus W. Now the trick in these problems is going to be to make sure that we have the correct signs for Q and W, because we don't necessarily directly give you the sign of those in the problem itself. We use the terminology. It helps us decide if it's positive or negative. And also we have to make sure the two are in the same unit before we add them together. So I've been harping for the entirety of this semester, now you're probably tired of hearing it, that we should always keep close track of our units, and it's true in this problem as well, because if we just add the two numbers together, if they're not in the same unit, it won't work, okay? So we're going to figure out what this Q and W is. So the first thing we look at is, in the problem it says we're absorbing 965 joules of heat. So anytime heat is absorbed, does that make it positive or negative? Positive, so that means it's going to be plus 965 joules for Q. So that is going to be a positive number. And then we also say that it has 456 calories of work done on it. So if we're doing work on the system, is that positive or negative? Also positive, so that's going to be plus 456 calories. But we want to get these into the same unit. The final one we want is in kilojoules, as it turns out. So we're going to convert both of these to joules first. So it's plus 456 calories for work. We have to convert to joules using 4.184 joules per calorie. All right, so that's given to us here. So in joules, this comes out to 1908. And then we can add the two together. So Q plus W is 965 joules for Q, plus 1908 joules for W, which is 2,873 joules. We want this in kilojoules, so we divide that by 1,000 to get 2.87 kilojoules. All right, so really in these first two questions here, calculating W, which we had to do individually on the first one, or calculating delta E as a sum of Q and W, the math is pretty simple. The equations are very simple. Oftentimes it's just getting the right signs and the right units that's the part you have to think a little bit about. Question?
What causes it to be negative?
So the wording would be if it releases heat, that's negative. So if instead of absorbing heat, it releases heat, that would be a negative Q. And then if it's work done by the system, so if the system is doing work, as it was in the first problem where it was expanding, for example, that would be an example where you have negative W. So it's either work done by, work done on, is the distinguisher, or heat absorbed, heat released. Those are the two sort of different terminologies you'll see. Other questions? All right, we'll go on then to the next one. All right, so some of the questions on the test, like this one here, are more sort of conceptual questions about delta H and delta E and things of that sort, not requiring us to do any real calculations here. So this one is about the reaction between HCl and NaOH, which we talked about a lot in Chapter 6, acid-base chemistry. And we're telling you here that it's exothermic, so that's the key word in this problem. Which of the following statements then is correct, knowing that it is an exothermic reaction? All right, so we're going to think about these answer choices one by one. So choice A, delta H is positive. So if it's an exothermic reaction, what would be the sign of delta H? Negative. So that one's wrong, because delta H should be negative for any exothermic reaction. So that's not going to be our answer choice. We're looking for the correct statement here. Choice B, the enthalpy of the products are greater than the enthalpy of the reactants. So this one we don't often think about in exactly these terms, but knowing the definition of delta H, remember that delta always means final minus initial. And if we're talking about a chemical reaction, the initial state is your reactants, the final state is your products. So delta H, even though we don't normally calculate it this way, is going to be the enthalpy of the products minus reactants. And as we already established in the first analysis that we did, this has to be less than 0 for an exothermic reaction. So if we move H reactants over, we just do a little bit of algebra to move it over to the other side, what we find is that the enthalpy of the products are less than the enthalpy of the reactants for an exothermic reaction. And this one says that they are greater, so that's wrong also. So choice B is also incorrect. Should be the opposite. In an exothermic reaction, the enthalpy of the products are less than reactants. Or another way to think about it is if the enthalpy is decreasing, because delta H is negative, that means enthalpy is decreasing, that means your enthalpy must be lower in the products than in the reactants for that to be true. Okay? So that's choice B is out. Choice C, if we think about the temperature of the surroundings, so remember in an exothermic reaction, the exo tells us that heat is being released. And anytime heat is being released, that means the temperature of the surroundings increase. Okay? Because anytime we have any sort of heat transfer, we have the system, if it releases heat, that heat will be absorbed by the surroundings, and if the surroundings are absorbing heat, their temperature will go up. So anytime you carry out an exothermic reaction in aqueous solution, for example, the temperature of the water increases because you're releasing heat into the solution. Okay, so that one is actually going to be true because in any exothermic reaction, the temperature of the surroundings will increase. All right, so that one we think is going to be our answer choice. Let's verify that the last two are also incorrect. So D is talking about the bonds in the products. So the bonds in the products are weaker than the bonds in the reactants. So we probably also haven't seen it in exactly these terms yet. But remember back from chapter 3, we learned that we called it delta E at that time, but really it was delta H. We just hadn't introduced delta H yet. So the enthalpy change, or the heat for a reaction, or however you want to think about it, can be approximated as the sum of the bond energies of the reactants minus the products. So we'll do a problem like this next week on the final exam review. But we learned this back in chapter 3, so we're going to sort of combine that with our knowledge now of delta H, which is that if we want to use bond energies, it's reactants minus products. And again, this whole thing has to be less than 0 because it's an exothermic reaction. So if we rearrange the inequality, what we find is that, right below it, someone around our room here, the bond energy of the reactants will be less than those of the products. So it's the opposite of what we saw for enthalpy. All right, so anytime you have an exothermic reaction, did I screw that up? Yes, I got that wrong. It's greater than reactants. Yeah, that's right. Okay, sorry. I wrote it opposite in my notes, so I was confusing myself. So bond energy of the products would be greater than reactants for an exothermic reaction. Choice D simply said they're weaker, so that's also incorrect. All right, so anytime you have an exothermic reaction, you have stronger bonds on average in the product than the reactants. Because when you form a bond, that's an exothermic process. So if the overall reaction is exothermic, that would only be true if the bonds that you form in the product side release more energy than the bonds you break on the reactant side. So that would mean that the bonds in the products are stronger for an exothermic reaction. So that's another way of thinking about the same thing, sort of like we talked about in choice B. And then finally, choice E, the reaction absorbs heat from the surroundings. We kind of already talked about this when analyzing choice C. So in an exothermic reaction, heat is released to the surroundings. All right, so that's what exothermic refers to, is releasing heat to the surroundings, exo meaning out from the system to the surroundings. So this one is also wrong because heat would not be absorbed, it would be released. So choice C is the only one then that is correct after going through all of them and finding that. So any questions on this concept or this question in particular? All right, so again, be prepared for at least one conceptual question about enthalpy. Most of the stuff we're going to do in this section is all, calculations, calculating delta E, delta H, calorimetry, all that stuff that we'll get to a little bit later, but there is going to be at least sprinkled in there a couple conceptual questions, so make sure you have some of those concepts down as well. All right, on to number 4. All right, so number 4 gives us a thermochemical equation where we have it's the combustion of ethane, C2H6, so ethane plus oxygen making CO2 and water with the correct coefficients, delta H given as negative 2,855 kilojoules. So we want to know what is the enthalpy change in kilojoules when 12.5 liters of ethane measured at 25 degrees Celsius and 780 torr is burned in air. Give your answer with one decimal place and no units. So this question actually combines Chapter 7 topics with Chapter 8. There won't necessarily be a lot of questions on the exam that do this, but for the purpose of the review I will, so that allows us to cover more material that way. All right, but we should be able to do this with what we know from both of those sections in the course. So we want to know, again, how much enthalpy change we have when we burn 12.5 liters of ethane at those conditions. So remember that in the thermochemical equation, what we're giving you here is a balanced chemical equation with a delta H. And the way that we interpret this is when 2 moles of C2H6 reacts with 7 moles of oxygen to make 4 moles of CO2 and 6 moles of water, the enthalpy change is minus 2,855 kilojoules. What we're asking in this question is what is the enthalpy change when we burn this specific amount of C2H6? So what we really need to be able to do then is first find the moles of C2H6 that we have. If we know how many moles of C2H6 we have, we can relate it to the thermochemical equation to find what is delta H for that many moles and treat it almost like a stoichiometry problem. So in this type of question, our first step is going to be to find the moles of our reactant that we're burning in this case. And because it's a gas, it's going to obey the ideal gas equation, PV equals nRT, which we'll see a lot more later on. And so we can use PV equals nRT for any gaseous reactant if we know the pressure, volume, and temperature to find the number of moles. All right. Now to do this, we need the pressure in atmospheres because we're going to use R. So we're going to solve for a number of moles, which is PV over RT. Because this calculation is going to use the universal gas constant R, we want our pressure to be in atmospheres for this. So we again have to do that conversion that we did earlier of taking our pressure in torr, which is 780 in this case, and dividing by 760 to get in atmospheres. So that comes out to 1.03 atmospheres, so not too different than 1 atmosphere. And now we can solve for moles of ethane by using PV equals nRT. So the moles of C2H6 is equal to its pressure, which is 1.03 atmospheres, the volume, which is 12.5 liters, divided by RT. R, we're going to use the universal gas constant 0.0821 liter atmospheres per k mole. This is the one that we use anytime we're doing calculations with gases. And that's on your periodic table, so you don't have to memorize it. And then the temperature needs to be in Kelvin, so we're at 25 degrees Celsius. And as a reminder that we're going to have to do a lot of times today, for any of these calculations involving gases, you also need temperature in Kelvin. So we add 273 to 25 and get 298 Kelvin. All right, so that's how we're going to calculate moles of C2H6, and what we come up with is 0.526. All right, so once we know the moles of one of the substances in the chemical reaction up here, we can relate that to delta H in a way that would be very similar to what we did in stoichiometry. So we're going to calculate delta H for this reaction where we have 0.526 moles of C2H6. And then we want moles of C2H6 to cancel out, so we're going to put that in the denominator, and we're going to solve for how many kilojoules of heat that represents. So we use the numbers in the balanced equation. There's minus 2,855 kilojoules for every 2 moles of ethane because we have a coefficient of 2 in front of C2H6. We have to remember to look at the coefficients to tell us what goes down here. That's per 2 moles of C2H6. And that gives us then into kilojoules of heat, which is minus 750.9. Typically in Blackboard entered without units if it's a numerical question. Okay? So for these types of problems with thermochemical equations, we often treat them a lot like stoichiometry. We have a chemical equation that relates moles of substance to delta H, heat released or heat absorbed, and we use that as a ratio here to solve for what the delta H is for a specific amount of substance. So other common variations on this would be, here we gave you a gas phase reactant, use PV equals nRT, but any other way that we know to find moles could be in play here. So we could give you the mass of the reactant and you have to use molar mass to find moles, or we could give you the molarity and the volume of a aqueous solution and use it to find moles. So it's really mostly what you're doing here is stoichiometry. It's just this one little key step here of using the delta H for the chemical equation as a conversion factor to figure out how much heat is involved in that process. All right, so any questions on that? Okay. So we'll move on then to number 5. So number 5, we're taking a 5-gram copper slug, just a piece of copper, with a heat capacity of 0.385 joules per degree Celsius, and we're heating it to a temperature of 100 degrees Celsius. It's placed into a cup of water with 10 milliliters in it, initially at 23 Celsius. What is the final temperature, assuming that no heat is lost? All right. So for these questions here, what we have to remember is that sort of the overarching concept is that we have two different objects, two different things at different temperatures, right? Our copper is initially at 100 degrees Celsius. Our water is initially at 23 degrees Celsius. Anytime you have that situation, you're going to have heat transfer between them. The heat from that is going to be transferred from the object that's hotter to the object that's colder, and the magnitude of that heat is going to be the same for both. So in other words, the heat for our system is equal and opposite to the heat for the surroundings. So that's true for any heat transfer process. And when we're doing a sort of experiment like this that involves a calorimeter, or a cup of water as it is in this case, where we're sort of measuring the temperature change, remember that the heat for our system is going to be absorbed by the calorimeter. So it's really, we can think of it as the heat for calorimeter, as we often abbreviate it in class. So in a calorimetry type problem like this, even though we didn't specifically say this is a calorimeter, but it's just a cup of water, which is the sort of world's simplest calorimeter. In that type of experiment, the calorimeter is your surroundings. So whatever heat is being lost from the system or being absorbed by the system is either being transferred to the calorimeter or being absorbed from the calorimeter. So those two terms are equal and opposite. And remember then that in this problem, the system is going to be the piece of metal that we're measuring. So the heat that's for the copper is going to be equal to the negative Q for the calorimeter. And the heat for a calorimeter, remember, is equal to the mass of water in the calorimeter times the heat capacity times delta T. So our calorimeter is going to have water in it in most cases. And then we also have to consider the heat that's absorbed by the calorimeter itself in some cases, which is the heat capacity of the calorimeter times delta T as well. And for any problem that involves calorimetry or heat transfer, we look at what information is given in the problem to tell us if we're going to use one or both of these two terms here. All right, so in this problem, do we know how much water is in the calorimeter? Anybody see it? Yes, it's there. So 10 milliliters of water. Do we know what the heat capacity of our actual calorimeter is? We don't have that information. So we're going to basically ignore this term, and we're assuming in this problem that all of the heat is absorbed by the water. All right, so if we don't tell you what the heat capacity of the calorimeter is, you can't account for what percentage or what portion of that heat is absorbed by the calorimeter. You just assume it's all absorbed by the water. So that means in this case then, the heat that's released by copper is equal to the negative of the heat that's absorbed by the water. So for copper, it's going to be mc delta T for the heat. So it's going to be mass of copper, heat capacity of copper times delta T for the copper is equal to, we have to put a minus sign up front on one side of the equation. Doesn't matter where the minus sign goes, but it has to be on one side of the equation. And our calorimeter is just going to be mc delta T for the water. And what we're solving for here is the final temperature. So both of them are going to have the same final temperature because the heat transfer stops once they get to the same temperature. So we can start plugging things in now. So we have 5 grams of copper is our mass for copper. The heat capacity of copper is 0.385 joules per gram degree Celsius. And then delta T we're going to rewrite as T final minus T initial. We're going to solve for the final temperature. So we have final minus initial. The initial temperature for the copper is 100 degrees Celsius. So it's going to be T final minus 100 Celsius. And that's going to be equal to the negative of the mass of water, which is 10 milliliters is 10 grams. Remember, the density of water is 1. So if we give you milliliters of water, that's the same as grams of water. Heat capacity for water is the one that we expect you to know, which is 4.184. And then delta T for water is final temperature, same final temperature, minus the initial temperature for the water, which is 23 Celsius. Okay? So this is the equation we're going to solve for, and we're going to solve for final temperature, which appears on both sides. We'll have to do some distribution and simplification. And I'm not going to go through all the algebra. What I came up with was the final temperature is 26.39 degrees Celsius. Again, asking for a numerical answer, so we would just enter in 26.39. Okay? So there's some algebra involved, but hopefully you guys can all follow that on your own. The other thing to keep in mind with this problem is that whenever you're doing a problem like this where you're solving for final temperature involving in any sort of heat transfer process, your number should be in between the two initial temperatures. So the initial temperature for water was 23, the initial temperature for copper was 100, so your temperature that you solve for at the end should be in between those two. If it's not, then you can know right off the bat that you made a mistake. All right, so that's how we're going to approach this one. It's just setting the heat for the system equal to the negative heat for the surroundings. In this case, we're treating the surroundings as just the water in the cup that we're placing it into, and no other details are needed. All right, questions on that? Yep. Well, I crossed out the whole thing. So this whole term here is heat capacity of the calorimeter times delta T. If we don't know what the heat capacity of the calorimeter is because it's not given to us, we don't include that term. We just assume that all the heat is absorbed by the water. So we're just leaving this whole term out here, okay? Now, I think I accidentally erased it, so it's gone forever. Other questions? Sorry. Assuming no heat is lost basically means that we can use this equality here. Because if heat was lost, if heat was leaking out of the cup of water into the air or whatever, the final temperature that you get would be different, but we can't really easily account for that. So that's just an experimental assumption where you're assuming that you have perfect heat transfer, perfect insulation of the rest of the surroundings, and that's just to make sure that equation is true. All right, other questions? All right, so let's go on to the next one then. So number 6 is sort of the other major type of calorimetry problem, which is studying a chemical reaction in a calorimeter. So we have a heat capacity with, calorimeter with a heat capacity of 9.25 kilojoules per Kelvin, and is filled with 1 liter of water. We have a 5-gram sample of acetic acid burned, which raises the temperature by 5.4 degrees Celsius. Use this information to determine the enthalpy change for the combustion of acetic acid, which is shown here in kilojoules per mole. So again, enthalpy change per mole of acetic acid. So this is a pretty typical calorimetry problem. The first thing we're going to do in all these calorimetry problems involving chemical reactions is we're going to calculate the heat for the calorimeter. All right. So the heat for the calorimeter, as we said in the last one, is going to be the heat that's absorbed by the water plus the heat that's absorbed by the calorimeter itself, which, as we said, is equal to the mass of the water in the calorimeter times heat capacity of water times delta T, plus the heat capacity of the calorimeter by itself times delta T. And we, as usual, have to look at the information in the problem to determine are we going to use one of these two terms or both of them, okay? So if you look at this problem, we're telling you that we have 1 liter of water, so we know, again, the amount of water in the calorimeter, so we're going to include that. And we also know that the heat capacity of the calorimeter by itself is 9.25 kilojoules per Kelvin, so we have to include that term as well. So in this case, we're going to use both of those terms to calculate the heat absorbed by the calorimeter. So here we're, again, not making the assumption that all the heat is absorbed by the water, but we have to also include the heat that's absorbed by the calorimeter surroundings, whatever's containing the water. So putting numbers in for this one, then the heat for the calorimeter is equal to, we have 1 liter of water, which is 1,000 milliliters or 1,000 grams. So we have 1,000 grams of water. That's our mass for water, heat capacity of water. And here we do have to be careful with units again, as always, because this is in joules per degree Celsius or gram degree Celsius. And then our delta T, we're telling you that the temperature is increasing by 5.4, so our delta T is positive 5.4 Celsius. And then we're going to have the other term is going to be the heat capacity of the calorimeter itself. Let me leave a little bit of a space for reasons that will become clear, which is 9.25 kilojoules per Kelvin or degree Celsius. Remember that for temperature changes, delta T can be in Kelvin or Celsius. There's no distinction there. But this is kilojoules, as we said, and then same delta T, 5.4. So the two things have the same delta T. But what you'll notice is we have two different units. So the heat for the water is in joules right now. The heat for the calorimeter is in kilojoules. Our final answer we want in kilojoules, so let's convert this first term into kilojoules by dividing by 1,000. All right, so you could also just calculate these separately and then add them together, but before you add them together, they need to be in the same unit. That's true for any time you add. So what we get for this then is 72.5 kilojoules, okay? Or you could have done it in joules first, 72,500, and then divided by 1,000 at the end. But again, before you add them together, they need to be the same. So you either need to convert this first term to kilojoules or the second term to joules before you add them together. All right? So that's the heat for the calorimeter, 72.5 kilojoules. And then when we're studying a chemical reaction in a calorimeter, because again, the reaction is our system and the calorimeter is our surroundings, we have this relationship very similar to what we saw in the last problem, which is that the heat of the reaction is the negative of the heat for the calorimeter. So they're equal in magnitude, opposite in sign. Any heat that's released by the reaction will be absorbed by the calorimeter. And so that means our heat of reaction is minus 72.5. Okay? But this is the amount of heat that is released, or the delta H, when we burn 5 grams of acetic acid. Why is this doing this? Stop. All right, we're burning 5 grams of acetic acid. What we want is the amount of heat that's released when we burn 1 mole of acetic acid. We want it in kilojoules per mole. We want it to correspond to this chemical equation, which has 1 mole of acetic acid as a reactant. So what we're going to do then to find delta H per mole is we're going to take the heat of reaction that we determine from calorimeter and divide it by the moles of substance, in this case the acetic acid that we're burning, CH3COOH. All right, so we're going to take that minus 72.5 kilojoules, and we're going to divide it by the moles of acetic acid. So moles of acetic acid is going to be, we're burning 5 grams, and we know that we can use molar mass, which I don't think I gave you here. Oh, I did, 60.02. So we're going to divide by that molar mass to get moles. All right, so grams cancels out, and what we get is 0.0833 moles. All right, so we're going to divide the heat of reaction by the moles of substance, 0.0833, and that's going to give us kilojoules per mole, which is minus 870.3. All right. So this is a pretty standard boilerplate calorimetry problem. A few steps involved, but we're going to first calculate heat for the calorimeter using the water and the calorimeter itself. Both terms in this case need to be included. And then once we have the heat for the reaction, it's just the negative of that, and then we divide by moles of substance. All right, so any questions on this one? Now, one thing that I want you to also be aware of is that at times we will, in some sense, combine what we have in this question, question 6, with what we did up here in question 4. And so the way we would often see those, so this is another variation that you should be familiar with and know how to do, is that in some cases we'll give you a calorimetry problem like this, but instead of giving you the heat capacity of the calorimeter, or instead of giving you the delta T, we will have you solve for one of those at the end. And so basically you're going to work backwards in that case. So there will be variations on this where we'll give you the chemical equation, we'll give you the delta H. So you're going to basically do this type of process using moles of substance and delta H to find heat of reaction. This delta H could be also thought of as heat of reaction in the context of a calorimetry problem. You're going to use this to find delta H, heat of reaction. And then what you're going to do is put it back and work backwards to find heat for the calorimeter, which is the negative of that. Set that equal to these terms where either the heat capacity of the calorimeter or the delta T or something in this is one of your unknowns. So just be familiar with the idea that you might have to work backwards in some cases using sort of the steps that we did in question 4 to calculate heat of reaction like we did in question 4, and then backing up into here to solve for some unknown in this equation, usually a heat capacity or sometimes the delta T. All right? So any questions on this one particular or that set of operations in general? All right, so we'll go on then to number 7. All right, number 7 is one of the other major ways that we have for calculating delta H, which is using what's called Hess's law. So we want to calculate the enthalpy of formation for B2H6, and we're giving you 3 chemical equations here with known delta H. So we're giving you 3 thermochemical equations and asking you to find delta H for some other chemical equation. Now in this problem, we did not specifically give you the chemical equation that we're trying to find delta H for. But what we want is the delta H of formation for B2H6. What we have to be able to do is write the formation equation for B2H6. So remember, in a formation equation, we're forming that compound, 1 mole of that compound in particular. and we're forming it from the elements in their standard states. So the two elements that make this up are boron and hydrogen. The standard state for boron is just B solid, and then the standard state for hydrogen is what? H2, diatomic, H2 gas. So these are the two reactants, and we just have to balance from there. So it's going to be 2 boron plus 3 H2. So this is the formation equation for B2H6, and so the delta H for this reaction is equal to the delta H of formation of B2H6. All right. So when you write a formation equation, whatever that enthalpy change is going to be the delta H of formation for that compound. So what we're going to then do is we're going to take these three equations here, which I'll number 1, 2, and 3, and we're going to figure out how can we combine these three together to generate this equation here, and then we modify the delta H's appropriately, add them together at the end to give us this delta H, which is the delta H of formation. So now it becomes a typical Hess's law problem where we have to figure out how to combine these three equations. So if we look at the first reactant in this equation is 2 boron, and we see that boron appears only in this first equation that's here, that's given. So we're going to take 1/2 times that first equation. So if we have, this one has 4 borons in it, we only want to have 2 borons in the final equation, so we're going to have everything that's in equation 1. So we take 1/2 times the first equation, which means that we multiply each of these coefficients by 1/2 or divide them by 2, so that's going to give us 2 boron plus 3/2 O2 going to B2O3. And the delta H for this modified equation is going to be then 1/2 times the original delta H. So this first delta H is minus 2509.1. Because we multiplied all the coefficients by 1/2, we also multiply delta H by 1/2. And so we're going to take this number and multiply it by 1/2, and we get minus 1254.6. All right, so that's the modified delta H for that one. We see that our second reactant is 3H2, and finding where that appears, H2 only appears in equation 2. So we're basically looking for which of these equations do the reactants and products show up in. So H2 only shows up in reaction 2 here. It has a coefficient of 2. We want it to have a coefficient of 3, so how do we have to modify equation 2? Multiply by what? 3/2. So it's already on the reactant side, so we don't have to flip it, but we want to change the coefficient from 2 to 3, so we multiply everything by 3/2. So we're going to take 3/2 times equation 2. So that's going to give us 3H2 plus 3/2 O2 going to 3H2Os. And because we multiply the coefficients by 3/2, we also multiply the delta H by 3/2. So it's this number minus 571.7 times 3/2, which comes out to approximately negative 857.6. All right, and then the last one, we want B2H6 as a product in our formation equation. This third equation has B2H6 as a reactant, so what do we do to this third equation here? We're going to flip it. Okay, so if you have this on the reaction side, but you want it on the product side, you're going to flip the whole thing. And so when we flip it, we just switch reactants and products. So we're going to get B2O3 plus 3H2O going to B2H6 plus 3 O2s. And because we flip the equation, what happens to delta H? We take the negative of whatever that number is, so it becomes positive. So it's going to be negative delta H3, which is going to be positive 2,147.5 kilojoules. All right. And so now that we have the three modified equations, we can verify if we so choose. If we don't necessarily, I don't 100% trust myself ever, so I'm going to try to make sure that I did this correctly and add them together. So we have 2 borons that carry through as reactants. Remember, we're going to take all the reactants, everything on the left side of the arrow, and add it together. Take all the products on the right side of the arrow. Anything that appears on both sides of the arrow cancels out. So 2 borons goes through, but if we look at O2, we have 3/2 plus 3/2. That's 3 O2s on the reactant side, but we also have 3 O2s on the product side. So all the O2s cancel out as they should. Our next reactant is 3H2, so that's going to carry through. And then in this third equation, we have on the reactant side B2O3, but that's going to cancel out with that B2O3 that's a product. We have 3 H2Os, but those are going to cancel out with those 3 H2Os. So those are the only 2 reactants that are left. And the only product that's left standing is B2H6. So we've gotten the correct chemical equation that we want, which is 2 boron plus 3 hydrogen going to B2H6. And then the delta H for this, which is delta H of formation of this compound, is going to be just these three numbers added together. Minus 1254.6 kilojoules plus minus 857.6 kilojoules plus 2,147.5 kilojoules. When we add those all together, we get a positive 35.3 kilojoules per mole, or just kilojoules. It's fine. This can be thought of as kilojoules per mole because it's 1 mole of substance, as it should be. All right, so we got 35.3. That's answer choice B right there. All right, questions? All right, so let's, yes, go ahead. So, on the reactant side, we have 3 halves O2 plus 3 halves O2 from the first two equations. So that's 3 halves plus 3 halves is a total of 3. And then that's going to cancel with these 3 that's on the product side. Okay. All right. Anything else? All right, on to the next one. All right, this question also deals with enthalpy of formation. We want to know the enthalpy of formation for NH3, given that we have the enthalpy of formation for NO2 and H2O given as well as this thermochemical equation. So this one we could also do the same way if we wanted to. We could write out all the formation equations and figure out again how to combine those formation equations with this to get the formation of NH3, but there is a shortcut we can do here because we have delta H for a reaction. Everything that's given to us is a formation equation. We're trying to find another enthalpy of formation, so we can just use the sort of equation form of this, which is that the delta H for any reaction is equal to the sum of the delta H's of formation of the reactants multiplied by their products first in this case. I always mix that up. And please don't do what I did. So it's products minus reactants when we're using delta H of formation. Sum of the delta H of formation for the products. Again, these M and N are the respective coefficients that we need to include as well. All right. So because in this problem we're exclusively dealing with delta H of formation, we're trying to find an enthalpy of formation. We're given 2 enthalpies of formation. We have just one other type of reaction given. The previous problem we didn't really have any formation equation except for the one we were trying to find, so we couldn't use this shortcut. All the given information was a different type of reaction. But we're going to use this here. This equation is always one we want to think about whenever we're dealing with enthalpy of formation. And as long as we have enthalpy of formation for everything, we can use it. Now in this case, what we're doing is we're giving you the delta H for the reaction, which is that number there, and we're trying to find the enthalpy of formation for NH3, which is one of the reactants. So in this case, one of the enthalpies of formation of the reactants is going to be our unknown, not the delta H for the reaction, which is given to us here. All right, so that minus 1134.4 kilojoules is going to be equal to the sum of the delta H's of formation for the products. So on the products, we have 4 NO2s. So we're going to multiply 4 times the delta H of formation of NO2, which is this number here, 33.2. On the product side, we have 6 H2O, so we're going to take 6 and multiply it by the delta H formation for water, which is minus 241.8 for water vapor, as it is given here. And then we're going to subtract from that the sum of the delta H's of formation for the reactant. So on the reactant side, we have 4 NH3s. That's our unknown delta H of formation that we're trying to solve for. And then we also have 7 oxygens. What's the delta H formation for O2? Is it given to us? Does it have to be? Did I forget to give it? No. What is it? 0. So any element in its standard state has enthalpy formation of 0, so we can all but ignore it. So this whole term is just 0 for the other reactant. So our only unknown then is delta H formation for NH3. So we do a little bit of algebra and solve for that and get that. The delta H formation for ammonia, NH3, is minus 45.9 kilojoules, which is choice A. All right. So we can use this equation up top to often find the delta H for a reaction when we know the delta H is a formation for all the products and reactants. In this case, though, we do not know one of the delta H formations, so we're going to solve for that as our unknown. Any questions on this one? Yeah. So that's the delta H formation for O2 gas. This is an element. And so for any element in a standard state, the delta H of formation is equal to 0. Okay? So that's true for any element in the standard state that shows up in the chemical equation. You can basically ignore it for delta H calculation. It's not that it's not there, it's not that it's not important, it's just that for calculating delta H using delta H as a formation, you don't need that for the element because it's always 0. Anything else? All right, on to number 9. All right, this question here, there's not a high probability you'll get one like one on the exam, but there's a few in the question set that deal with this. This is basically just all kinds of conversions here, and it's talking about burning a fuel, methanol, which has a molecular weight of 32. So the combustion enthalpy of the methanol is minus 715 kilojoules per mole, which means that we're going to release 715 kilojoules of heat or energy every time we burn that. And it has a density of 0.792 grams per milliliter. And what this question is asking is if we burn 1 liter of methanol to produce electricity, how long would it power a 60-watt light bulb, assuming 100% efficiency? And the other key conversion we gave you is that 1 watt is equal to joule per second. So really, this question here sounds kind of complicated. It's like, what do we do with all this information? But it's really just dimensional analysis. It's figuring out, what information are we given, and then how do we use all the rest of the information as a conversion factor to go from one step to the next. So what we're looking for here is the amount of time. And this question I set up in a very annoying way because all the times are in different units. So I apologize for that because I already don't like me, so that's not going to change anything. So the time is what we're looking for, and we're figuring out how long will this light bulb last if we burn 1 liter of methanol as the fuel to provide the energy for the light bulb. So we're burning 1 liter of ethanol. So we have 1 liter of C4H4O. And then what we're going to do is we know that the combustion enthalpy is in kilojoules per mole, so we're going to convert that to moles first to be able to figure out how much energy is released when we burn that much methanol. So this is kind of similar to what we did in a previous problem where we're using, again, moles of substance and an enthalpy change per mole to calculate amount of heat that's released or amount of energy that's released. All right, so we're going to convert this to moles. We're going to do that in 2 steps. We're going to convert to milliliters first. Or I guess 3 steps, technically. So 1,000 milliliters per liter. Once we have milliliters, we know that the density is 0.792, so we're going to use that to calculate grams. So 0.792 grams of methanol is 1 milliliter. That's what the definition of density. So milliliters cancel out. Now we have grams, and once we have grams, we know how to convert to moles because we do it all the time in this course, which is taking the molar mass and dividing by that. So 1 mole of C4H4O has a mass of 32 grams, which I think might be wrong. Is that 30? No, I think 32. Oh, God, this is the problem. That's the wrong formula for methanol. Man, what a horrible typo. It's just CH4O, that's why. I was going to say that molar mass doesn't look right. It's not right because the formula is not C4H4O, it's CH4O. All right, so now that makes more sense, it's 32 grams per mole. So let's get rid of that 4 as well. So it doesn't really change how I do the problem, it's just that I had some unfortunate typo in the word problem. All right, so now we have moles of CH4O, and that's going to give us the amount of substance, and then we're going to use the combustion enthalpy, which is in kilojoules per mole, to figure out how much energy is produced when we burn that much methanol. So once we have moles of substance, we can use 715 kilojoules. It's technically negative for the combustion enthalpy, but that's telling us that we're producing 715, so we don't have to think about it as a negative number here, because it's just the amount of energy that we're releasing that we're interested in. CH4O. So that's kilojoules per mole, which is that number there. And then the last thing we're going to need is the wattage of our light bulb is 60, which is number of joules per second. So we have to convert kilojoules into joules. And then once we know how many joules of energy we're producing and giving to the light bulb, we can then use the wattage of the light bulb to figure out how long it will burn for. So 1 watt is 1 joule per second. So if we want to convert from joules into a unit of time seconds, we divide by the wattage. So it's 60 joules per second for this light bulb because it's a 60 watt light bulb. That's probably the most common light bulb that you would find in your house, at least at the time when we still used incandescent light bulbs primarily. All right, so that gives us the number of seconds, which is 2.95 times 10 to the fifth, which doesn't match either that answer choice in seconds. If we divide by 60, we get 4.9 times 10 to the third minutes. So we're just dividing each of these by 60 to go from seconds to minutes to hours. That doesn't match the answer that's in minutes. And then finally, if we divide by 60 one more time, we get 81.9 hours. And that's the number then that will match answer choice D here. All right, so we had to go through a few different units because the answer choices are mixed, but we get 81.9 hours. So if we burn 1 liter of ethanol to produce electricity or energy, and we give that to a light bulb, assuming that there's 100% efficiency, we would be able to burn the light bulb for about 3 days, 81.9 hours, about 3.5 days. All right, so this was just as I said, mostly a dimensional analysis unit conversion problem. Some of these we use all the time, some of them are less common for us, but if we just, again, look at the units that are involved with each of these, we can piece it together in this way. So any questions on this? All right, on to the next one then, number 10. All right, so we finally moved on then. If you're keeping track of where we are, we're into chapter 8 stuff now with gases. So this is the first question dealing with ideal gas behavior. So we have a balloon filled with an ideal gas. It has a volume of 253 milliliters at 24 Celsius. What is the volume if the temperature is increased to 86 Celsius? So this is one of those typical classic types of problems where we have an ideal gas and we're changing one or more of the, or I guess at least two of the parameters for that gas: pressure, volume, number of moles, or temperature. So for any of these problems, we have some of these individual relationships that are possible to use, but we can always start with PV equals nRT. So there's the 3 individual gas laws we covered. There's Boyle's law, Charles' law, Avogadro's law. We could remember those individually, and at least for some conceptual questions, it might be necessary to. But in any type of gas law problem, we can always start with PV equals nRT because that's the combined equation for all the entire state of a gas. And then we just derive the equation that we need. So in this question, we're looking for volume, so the volume is changing, and we're also telling you that we're changing the temperature. So we're going to assume then, because we're not told otherwise, that the number of moles is the same. In other words, there's no leak in the balloon, so we have the same amount of gas, and the pressure is the same because we're not told anything about the pressure changing. So we take everything that's changing and move it over to one side, so we get volume over temperature, or temperature over volume, would work either way. And then we move everything else to the other side, so that's going to be nR over P, and that's our constant. So number of moles is constant, pressure is constant, R is always constant. So these are the two that are changing, which means that ratio of volume over temperature is going to remain constant before and after. So V1 over T1 equals V2 over T2. So in any of these types of problems, you separate out the parameters, the variables that are changing, and you set the initial and final equal to each other like we did here. All right, so we have this. This is technically Charles's law, but we don't need to even know that for this problem. We can just derive the correct equation starting with PV equals nRT. So what we're solving for here is V2, the final volume after we've increased the temperature. So that's going to be V1 times T2 over T1. And we start putting things in. So our initial volume was 253 milliliters. For these types of problems, the units don't matter. It wouldn't be wrong to convert to liters, but we don't have to because we're not using the universal gas constant R in this. It's just whatever volume we use, we just attach the units to it. The only thing that's non-negotiable, as we've talked about, is temperature. So both these temperatures need to be in Kelvin. So the T2 is going to be 86 degrees Celsius, and we add 273 to that to get it into Kelvin. So that's going to be 359 Kelvin. And then T1 is 24 degrees Celsius. We add 273 to that and get 297 Kelvin. So we've already used Kelvin temperatures earlier today, but this is a little bit more detail of how we do that. We just add 273 to go from Celsius to Kelvin, and that step is, again, necessary. There's no way to skip that. So it's going to be T2 is 359 Kelvin, T1 in the denominator is 297, and what we get is a volume of 306 milliliters, which corresponds to answer choice C. So our volume increases by roughly 20% when we increase the temperature from 24 to 86 Celsius. All right. I'm pretty sure answer choice A is what you would get if you did not convert to Kelvin, which you have to do for this problem. So if anybody got 907, that likely means that you did not convert your temperatures into the correct units. All right, questions? All right, we're halfway there. Makes me think of Bon Jovi. All right, so number 11 now, more stuff with gases. So this time we have a steel tank with a fixed volume, so we're not changing the volume here. Volume is constant. So we want to, again, look at problems for keywords, and this is telling us that volume is constant. We're filling it with 126 grams of nitrogen at 298 Kelvin, and the pressure is initially 235 kilopascals. What will the new pressure in the same units be if we add another 96 grams and we cool the temperature to 273? So we're really doing two things here. We're starting with an initial sample of gas, that's 126 grams of nitrogen, 298 Kelvin, 235 kilopascals. We're adding more nitrogen and we're cooling it down. We want to know what's the effect on the pressure. All right, so we still are going to start with PV equals nRT. And this time the things that are changing, we said that volume is constant, so we're not going to worry about volume, but pressure is changing, that's what we're trying to find. Number of moles is changing, is because we're adding more gas to the tank. And the temperature is also changing. We know the two are from 298 to 273. So we're going to, again, derive an equation that involves those three units as the ones that are changing, those three parameters. So it's going to be pressure divided by NT is equal to R over V. This is one way to do it anyway. We just move everything that's changing to one side, everything that's not changing to the other. And so that ratio is going to be remaining constant, and that means the initial and final ratios P1 over N1 T1 will equal P2 over N2 T2. So this is not one of our typical gas laws. This is not, Avogadro's or Charles or anything like that. This is a combined equation that involves relationships between pressures, moles, and temperature that we can get from the ideal gas equation by moving everything to one side. All right, the reciprocals of these will work also. If you did it the other way, where you had N1 T1 over P1 equals N2 T2 over P2, you'll get the same answer anyway. So it's no big deal how you set it up. Either way will be fine. So what we're solving for here is P2, so let's figure out what we need for that. P2 is going to be equal to P1 times N2 T2 over N1 T1. All right, so just, again, solving for P2, which is what we're looking for. So we can start putting things in. P1 is given to us. Our initial pressure is 235 kilopascals. Now we need the two number of moles, N2 and N1, and we're initially giving you grams of substance here. So the initial number of moles N1 is going to be, we started with 126 grams of N2, and we just divide by molar mass of 28 to get into moles. So the ideal gas equation does not involve grams of ideal gas, it involves moles, so we have to convert to moles first. So we're initially starting with 4.50 moles, that's our N1. And then what we're telling you is that we're adding 96 grams of N2. So the N2 then is going to be the initial amount that we started with, 4.5, plus the amount that we're adding. So plus 96 grams of nitrogen converted to moles also. So N2 is not the amount that we added. N2 is the total amount that we have at the end. That's always going to be true for ideal gases. If you add gas or subtract gas, N2, the number of moles, is not the amount that you're adding or subtracting. It's the amount that you actually have after the addition or subtraction. All right, so we convert 96 grams to moles, and then we add it to the amount of moles that we started with, 4.5, so we get 7.93 moles. All right, so that's N1 and N2. So N2 is 7.93. And then the T2 is, the final temperature is 273. We're cooling it down to 273 Kelvin. And then in the bottom we have the initial number of moles, which is 4.5, that we just found earlier. And then T1, which is 298. And what we come out to then is numerically that's 379.4, and the units that are left is kPa for pressure, which is what we want. All right, so the number we would enter is 379.4. That is kilopascals because moles cancels, Kelvin cancels, and we're left with kPa. All right, so just another combined gas law. This time we had to use more than two variables. We had to use pressure, moles, and temperature, but we can still go about this the same way. All right, any questions on this? So there are other ways to do this. I'm not going to go through them in the interest of time, but this was one straightforward approach, I think, for getting to the answer. And however we do it, we do need to know how many moles of gas we have at the beginning and the end, because that's going to determine the ideal gas equation for both of those. All right, so number 12 is dealing with gas stoichiometry now. So we saw it a little bit earlier that once we have the ideal gas law, PV equals nRT, we can use that as a relationship to find number of moles, and we can do stoichiometry with that as we did in chapters 5 and 6 earlier. So in this case, we're going to think about those same concepts. So we have NO and Cl2 reacting to form NOCl. So we need to start with a balanced equation. So we have Cl2, so we're going to have 2 over there, 2 NOs, so we put 2 over there. All right, and all these are gases. All right, so that's going to be important for this question. So we're taking 32.5 liters of NO and 21.2 liters of Cl2. We're reacting them at STP. So I think I failed to introduce this in class, I keep forgetting to do this, but I think you've all seen it by now. STP is standard temperature and pressure, which is 273 Kelvin and 1 atmosphere of pressure. So anytime you see STP, that means that's the temperature and that's the pressure. So make sure we're aware of that. So in this problem, we tell you that we have 32.5 liters of NO and 21.2 liters of Cl2. So what's the first thing we have to do if we know amounts for two reactants before calculating how much product is formed? So we're gonna potentially use moles, but what do we have to figure out about the two reactants? Which one's the limiting reactant? So anytime we tell you the amounts of two reactants or more than two reactants, you have to first determine what the limiting reactant is. So one way to do that would be to use PV equals nRT and rearrange it and find moles of each reactant. And that would work in this case, especially because we gave you the temperature and the pressure, STP. However, we could also take a shortcut in doing this because we're at the end looking for the volume of NOCl that forms in liters. So if we convert to moles first, we're going to have to convert back to liters at the end, so we're going to basically undo what we did using PV equals nRT. So a shortcut is to recognize that the volume that we're reacting is proportional to the number of moles. So they're both, in the numerator in this equation when it's written in this form. And so that means the number of liters that you have is proportional to the number of moles that you have if everything's at the same temperature and pressure, which tells us that we can treat these coefficients also as volume ratios. They are mole ratios, but they can also be thought of as volume ratios, where at a given temperature and pressure, 2 liters of NO plus 1 liter of Cl2 will make 2 liters of NOCl. And so we don't necessarily have to convert to moles first. We could, it would still work here. There's no reason that we couldn't do it, but it would take more time. So if we want to find limiting reactant, all we really need to do is just take the volume of each reactant and divide it by the coefficients, because the coefficients are also volume ratios anytime we're dealing with gas phase reactants and products. This only works for gas phase reactions. It's not going to be true for aqueous or solid phase or anything like that. But if everything's in the gas phase, pressure, volume, and number of moles are all related to each other, so we can treat those ratios equivalently. So if we want to find the stoichiometric ratio for NO, the way that I prefer to do it for finding a limiting reactant, we just take the volume of that and divide it by the coefficient, which is 2. So we get 16.25. And then for Cl2, to find its stoichiometric ratio, we take the volume of Cl2, which is 21.2 liters, divided by the coefficient, which is 1, and we get 21.2. And the smaller of these two, just like it would be if we were dealing with moles, the smaller of these two gives us the limiting reactant. So this number is smaller, so we know that NO is the limiting reactant. And then if we want to calculate the volume of product that forms the liters of NOCl, we can do that directly now without even going through moles. So liters of NOCl is going to be 32.5 liters of our limiting reactant NO, which is our starting point, and then we're going to use these coefficients as volume ratios for a gas phase reaction that works just fine. So 2 liters of NOCl is going to form for every 2 liters of NO reacts because they both have coefficients of 2. And so that's just going to give us the same number, 32.5 liters of NOCl. All right? So again, there's no reason why you couldn't have calculated moles of each reactant and then calculated moles of product and then use PV equals nRT again to go back into volume, but this saves us a lot of time if we just treat the volume ratio, the mole ratios as volume ratios. And in other problems, we might not give you the exact temperature and pressure. So notice we didn't use either of these numbers in the calculations. So this would have been true no matter what the temperature and pressure was, as long as all the reactants and products were at the same temperature and pressure. So if we set up a problem like this where we didn't tell you it was at STP, or didn't tell you that it was at a certain temperature and pressure, this would be the best way to do it again, because we can just use the volumes directly. All right, questions on that? All right, so that's, again, a shortcut method that can save you a lot of time in some of these gas phase reactions. All right, number 13 deals with a 250 milliliter gas bulb filled with 0.379 grams of a gas, again at STP, so we're using that same abbreviation STP, which tells us that our pressure is 1 atmosphere, our temperature is 273, so we know the temperature and pressure. Which of these is most likely to be the gas? So this problem sort of deals with the density of a gas, because we have the mass and the volume of the gas, so we know the mass and volume, that's density, and we also know from PV equals nRT we can derive an equation that involves density or involves the mass more generally. So if we start with the ideal gas equation, PV equals nRT, there are a couple of different ways that we can do this problem, but it's going to involve either finding the number of moles using PV equals nRT, or we can convert moles into a relationship involving mass. So we're trying to identify an unknown gas, so what we're going to try to find is what the molar mass of that gas is. So the two ways to go about this, we recognize that the number of moles is equal to mass divided by molar mass. So we can either find the number of moles first and then solve for molar mass using the mass that we're given, or we can just put this whole thing into the ideal gas equation, which is what we did when we derived the density equation, and say that PV is equal to mass divided by molar mass times RT. So remember, mass over molar mass is that common relationship we use for moles when we have grams of substance, so we can just make that substitution into the ideal gas equation. And then what we're solving for here is the molar mass of the gas, so we're just going to solve for this here, because if we know the molar mass of the gas, we can identify which of these it matches most closely with. So the molar mass is going to be given by mass times RT over pressure times volume. So we're just rearranging this equation to solve for molar mass. And then what we end up with is the mass of the gas is 0.379. That's how much we have in the container. R is the universal gas constant, 0.0821 liter atmospheres per k mole. And then the temperature here is 273 Kelvin. And pressure times volume on the bottom. So it's standard temperature and pressure, so our pressure is 1 atmosphere. And the volume is 250 milliliters. That needs to be in liters because we're using the ideal gas constant, which is in liter atmosphere. So we're going to convert 250 milliliters to 0.250 liters. And the number that we end up with is 33.98 grams per mole. So this will be in the correct units because we have grams here, we have moles there. Liters cancels, atmospheres cancels, Kelvin cancels. We're left with grams per mole, 33.98. So you don't have to change any of the other units to get to that. So we have to figure out which of these has a molar mass closest to 33.98. So if we do quick, rough calculations of molar masses, pH3 is 34, 31 plus 3. SO2 is 64, 32 plus 2 times 16 is 64. N2 is 28. And argon, just straight off the periodic table, is 40. So these are just the approximate molar masses of these four gases. The one that matches most closely is choice A, pH3. So this gas would be pH3. All right. So there are other ways we could have gone about this problem. We could have, again, figured out that molar mass is also just equal to mass divided by moles. So we could have found those two things separately and divided them. So there's a couple ways of getting to this as well, as we would see for most of these problems. Any questions on this? All right, one last shortcut that I'll introduce to you, but you have to promise me to be very careful to only use it at the right time, is that if we're at STP, standard temperature and pressure, 1 mole of any gas will have a volume of 22.4 liters. So this is yet another way we could have done this problem, which was to convert the volume into moles using this relationship and then divide mass over moles to get molar mass. So all get to the same answer. It doesn't matter how you do it, but we can use this. This relationship is going to sometimes be helpful as well. but you have to make sure you don't use it for any other conditions besides STP. Not for anything besides gases, not for any other conditions besides 1 atmosphere and 273 Kelvin. All right, so hopefully we're far enough along that that's not going to trip us up at all, but don't don't abuse this relationship, but you can use this to help you in some cases, and this would have been one of those where there would have been an alternative way of doing this problem that used that as a shortcut. All right, questions? All right, on to number 14. So number 14 is now dealing with mixtures of two gases. So we have one tank that has 3.25 atmospheres of nitrogen, the volume is 9.3 liters, and then we connect it to a second tank that has 5.33 atmospheres of oxygen, and its volume is 15.2 liters. So we open the valve and allow the gases to mix, and we want to know what's the final pressure. All right? So we should recognize that whenever we mix two gases together, what Dalton's law of partial pressures tells us is that the total pressure is just the sum of the partial pressures of the two gases. So it's going to be the pressure of nitrogen plus the pressure of oxygen. But we can't just use the two pressures we're given. These have to be the pressures that we observe after they're mixing together, because both of the gases are going to change their volume. Because initially they're occupying just one of their own tanks, but then when we mix them together, they're going to spread out and fill the entire available volume. So we can't just use these two pressures. We have to calculate what these two pressures are after the gases mix together. Okay? So that's how we're going to end up doing this. So for each gas that we have in the mixture, we can treat them separately. Anytime we have a mixture of two gases, they behave independently, because ideal gases, we assume that there's no interactions between them, no intermolecular forces. So we're going to treat each gas separately, and then for both of them, pressure times volume equals nRT. The number of moles of each gas is staying the same. The temperature for each gas is staying the same. So that whole thing is going to be equal to a constant, which means for each gas we're going to do Boyle's law. P1V1 equals P2V2. All right. So for each gas, they have their initial pressure, their initial volume, and when they mix together, they're going to have a final volume that's this combined volume of both containers that they're now allowed to move in between. And so for both of these, we're going to solve for the final pressure of P2, which is P1V1 over V2. V2 again being the combined total volume of the two tanks once they're allowed to mix together. And then once we have P2 for both gases, we can add them together to get the total pressure of the mixture. All right, so for nitrogen, our final pressure P2 is equal to P1V1 over V2. So the pressure and volume initially for nitrogen is 3.25 atmospheres, and the volume for the nitrogen cylinder was 9.30 liters. That's that number there. And then the final volume V2 for both gases is going to be the sum of the two. So once we mix them together, the combined volume of the two tanks is 9.3 liters is the first tank. The second one is 15.2 liters. And so the combined volume after mixing is going to be 24.5 liters. So for both gases, this is going to be their final volume V2. And so for nitrogen, the final pressure, the final partial pressure for nitrogen is 1.23 atmospheres. And then for O2, we do the same. The final pressure is going to be the initial, which is 5.33 atmospheres for O2. That's the number we were given for O2. The initial value for O2 was, the initial volume was 15.2 liters. And the final volume for O2 is again the combined volume of both, which is 24.5 liters. So for O2, we get 3.31 atmospheres as the final partial pressure. And now that we have the two partial pressures after mixing, we can just add them together. So it's going to be 1.23 atmospheres, which is the partial pressure for nitrogen, plus 3.31 atmospheres, the partial pressure for oxygen, and the combined pressure will be 4.54 atmospheres. All right. So both gases are changing their volume, so their partial pressures are going to change. But once we have both of those, we can just add them together to get the total pressure. Yes?
On the test, we didn't need to know, like, if that's Boyle's law or anything like that.
Potentially, yes. So it would be, there could be some, definition or conceptual type questions where we say, which of the gas laws deals with the relationship between pressure and volume, or what is the equation for that, and that would be Boyle's law. And you can always derive the equation from the ideal gas law, but you should know that pressure and volume relates to Boyle's. So there's only 3 of them that we learned. They all have volume involved too, so it's volume related to something else. So volume and pressure is Boyle's law, volume and temperature is Charles's law, and volume and number of moles is Avogadro's law. So those are 3 you should be familiar with. I don't think any of the other pairs even have names associated with them, or if they do, you're not responsible for those. All right, anything else? All right, onward and upward. Okay, number 15, we're dealing with gas effusion. So we have 2 atmospheres of nitrogen, and it diffuses through a small opening, so that basically means it leaks out, and it takes 2 minutes to leak. If a sample of an unknown gas under the same conditions takes 3.9 minutes to diffuse, or effuse, I guess is what that should say, but it's the same, really the same concept either way. What is this molar mass? Okay, so anytime we're dealing with diffusion or effusion, we have this relationship, this ratio of rates, where if we have 2 gases, nitrogen and some unknown X, as I'll call it, the rates of diffusion or effusion are related to the inverse of the molar masses. The molar mass of the unknown gas divided by the molar mass of nitrogen. So this would be true if we're dealing with rates of effusion, but here we're talking about the amount of time that it takes. So if you think about this conceptually, the gas that's leaking faster is going to take shorter time, so the one with the higher rate is going to have the smaller time. The one with the lower rate is going to take a longer time. So the rates and times are inversely related, which means that if we're dealing with times, we have to flip one side of the equation. So if we want to know then the amount of time that it takes nitrogen to effuse or diffuse over the amount of time that it takes our unknown, that's going to be given by the direct square root relationship of the molar masses. Molar mass of N2 divided by the square root of the molar mass of the unknown. All right? And so, when you do these types of problems, as I said, there's 2 forms of the equation, so you have to make sure you use the correct one. But thinking about it sort of logically or conceptually is helpful also. So we know that if a gas is heavier at the same temperature, it's going to be moving slower. So if a gas is moving slower, it should take longer to leak. So if our unknown gas takes longer than 3.9 minutes, it takes 3.9 minutes to leak, which is longer than the amount of time it takes for nitrogen, our unknown gas should be heavier than nitrogen. So when we go through and do all this, if we don't get a molar mass that's larger than that of nitrogen, we can know, at least just from our, from the concept of effusion and diffusion, that we didn't get the right answer. All right, so we're just going to use this now to solve for our unknown molar mass, which is given here. So the time that it takes for nitrogen is 2.0 minutes. The time that it takes the unknown gas to effuse is 3.9 minutes. And that's equal to the square root of the molar mass of nitrogen, which is 28 grams per mole, divided by our unknown molar mass, which is going to be what we're going to be solving for. All right, so then with a few cross multiplications and dividing and removing the square root by squaring and all that stuff, we get that the molar mass of our unknown is 106 grams per mole. All right, so we concluded that it should be larger than nitrogen because it's taking longer for that gas to leak out. 106 is larger, and that's going to be choice B, which is our correct answer in this case. Yep. No, that would be what you're doing if it's rate or distance. So remember that rate is proportional to distance over time. And these are inversely proportional to the molar mass. Sorry. Stop. I don't want to go in my mail. All right, so there's this sort of relationship. And so if you're dealing with rate or distance, this is the form of the equation when you use where they're inversely related to the molar masses. If you're dealing with time, they're going to be directly proportional to the molar masses. That's the correct one to use here. And you can think about that again as we know that, and from this relationship, but also just knowing the concept is helpful as well, the heavier the gas is, the slower it's moving. So if you're dealing with rates of effusion or how far something moves in a period of time, you want that to be inversely related to the molar mass. The heavier the gas, the slower it's going to move, or the less distance it's going to move in a given time. Whereas for amount of time, they're going to be directly related to each other, again by the square root, but they're going to correlate with each other in a positive sense. All right, any other questions? All right, move on to number 16. All right, this is a conceptual question about ideal gases. So we have a lot of numerical questions that we've seen, also some concepts that are going to be involved. And just a bunch of statements to try and figure out which ones of these are false. All right, so we have 4 statements to consider, so let's go through them one at a time, as I like to do for these, just to work through all of them. In a mixture of 2 gases A and B, the total pressure depends only on the total moles of A and B, not their identity. And this is going to be true for any situation involving ideal gases, because PV equals nRT. It just depends on number of moles. It doesn't depend on what the gases are or how many of them are mixed together. All you need is total number of moles. So in a mixture of gases, the total pressure is determined by the total moles of gas. It doesn't matter which gases they are. It doesn't matter what the ratio that they're mixed together in is. It's just determined by total number of moles. So this statement is going to be true. So we're not going to count that one as one of our false statements, which is what we're looking for here. All right, choice B. Samples of helium and O2 at STP have the same kinetic energy. So if they're at STP, that means they're both at 1 atmosphere and 273 Kelvin. And when we talk about average kinetic energy, that only depends on one thing. It's proportional with only the temperature. So if you know the temperature of the gases, doesn't matter what gas they are, they're going to have the same average kinetic energy. So if both of these gases are at the same temperature, they're going to have the same kinetic energy, so this is going to also be a true statement. Okay? They won't have the same molecular velocity. As we talked about in the last question, the molecular velocity or the rate of effusion or diffusion that comes from that would depend on the molar mass. But kinetic energy only depends on temperature. And so for these 2 gases, even though they're 2 different gases with 2 different molar masses, they will have the same average kinetic energy if their temperature is the same. And that's true for any gases. All right, choice C. Samples of helium and O2 at STP have different average molecular speeds. O2 is higher. So let's think about if this one is true. So at a given temperature, as we just said, the kinetic energy is proportional to the temperature. Kinetic energy is equal to 1/2 mv squared. All right? So these 2 gases will have the same average kinetic energy, but because kinetic energy is the product of mass and the square of the velocity, they won't have the same velocity. So whichever one has a larger mass or a higher mass is going to have smaller velocity, and vice versa. All right, so these 2 gases will not have the same average molecular speeds because, as we said, the velocity is proportional to 1 over the square root of the molar mass. That's where the equations came from that we used in the last problem. So heavier gases at a given temperature are going to have a slower speed. So in these cases, they will be different, but O2 should have the smaller. So this one's going to be false. Okay. So O2 has a molar mass of 32. Helium has a molar mass of 4. The one with the higher molar mass should have the lower average velocity. So this statement is false because that word there should be lower instead of higher. All right, so that's one of our false statements, and then choice D is the last one to consider. Deviations from the ideal gas law are smallest at high pressure and low temperature. All right, so when we're talking about deviations from the ideal gas law, remember that the ideal gas equation, the key assumption is that the gas molecules are not interacting with each other at all. There's no intermolecular forces, no attractions, no repulsions, no anything. And that's going to be, so if that's going to be true, you want the gas molecules to be as far away from each other as possible, and you want them to be moving as quickly as possible so they don't spend a lot of time sort of interacting or colliding with each other. So deviations from the ideal gas law are smallest when you have not high pressure but low pressure. That's because you want the gas molecules to be farthest apart, and you want the temperature to be high so they're moving around as quickly as possible. So this one again is false because it states the opposite of what should be the case, which is that deviations are smallest at low pressure and high temperature. So choice E is what we're going to pick. Both C and D are false. Okay. So deviations from the ideal gas behavior, if we're talking about it in terms of temperature and pressure, you want the deviations are going to be smallest when it's low pressure, high temperature, because that'll keep the gas molecules as far away from each other. We also know, having now gone through part of Chapter 9, that as you lower the temperature of a gas, eventually it's going to condense into a liquid. So the behavior as a gas becomes less and less gas-like the lower the temperature gets, and eventually it's going to have such strong intermolecular interactions that it'll become a liquid. So hopefully that makes a little bit of sense now, especially in light of what we've learned in Chapter 9 about intermolecular forces and phase changes and stuff also, which is not directly covered on this test, but does relate to this concept about deviations from ideal gas behavior. All right, questions? All right, number 17. So now we're back. We're in the last section of this, which is, and this is a pretty accurate distribution. So as you can see, there's only, 4 questions on Chapter 9. We're in Chapter 9 stuff now. which is only going to really be half of Chapter 9 covered on this midterm, and only about 20% of the test or so is going to be on Chapter 9. So it's a little bit more heavily weighted towards Chapters 7 and 8 than it is Chapter 9. That's pretty accurate. So the first question deals with intermolecular forces. We want to know which intermolecular forces are present in a sample of SF4. We have London dispersion forces, covalent bonds, dipole-dipole forces. 2 of these or all of these. So the first one, London dispersion forces, we can always consider because everything has London dispersion forces. Okay? Anything that's, well, as long as it has electrons, which is every chemical substance that we deal with. So anything that has electrons has London dispersion forces, so it doesn't matter anything else about the substance, what kind of substance it is, whether it's polar or nonpolar. None of this matters. It will have London dispersion forces. All right, so that one we can always include. The next one, covalent bonds. Do we want to select this as our answer? So SF4 does have covalent bonds, but covalent bonds is not an intermolecular force. Okay? Remember that covalent bonds are an intramolecular force. Those are forces that hold the atoms together in a molecule, but intermolecular forces are talking about the weaker forces that hold molecules together, that attract molecules to one another, especially when you're in a condensed phase like a liquid or a gas. So even though SF4 has covalent bonds, that's not classified as an intermolecular force, so we wouldn't want to pick that as one of our answer choices. Choice C, dipole-dipole forces. To figure out if something has dipole-dipole forces, it has to be a covalent compound, which this is, and it has to be a polar covalent compound. So we need to go back and review what we learned in Chapter 4 to figure out, is this molecule SF4 polar or nonpolar? So this will be a good refresher for the final exam that's coming up as well, because we will see questions about polarity on the final. So we have to draw a Lewis structure, figure out the three-dimensional VSEPR structure, and then determine if it's polar or nonpolar. So counting valence electrons, I'm not going to go back to the periodic table back and forth, but from the periodic table, sulfur's in group 6, so it has 6 valence electrons. Fluorine is in group 7, there's 4 of them, so they're going to be 7 valence electrons each. So this molecule should have 34 valence electrons. So we get S bonded to 4 fluorines. We complete the octets of the fluorines first. So that's 4 octets, which is 32. We have 34 total, so we're going to put 2 more on the central atom. All right, so that's the Lewis structure of SF4. Again, I went through it quickly because that should be reviewed, but I can answer any questions on it if you have them. This is AX4E using the AXE notation, and as we talked about, one nice helpful thing to remember for polarity is that anything that has one lone pair in the central atom will be polar. This is the seesaw geometry, but anything with one lone pair is polar. Okay? So because this is a polar molecule, this is going to have dipole-dipole interactions. Any molecule that is polar will exhibit dipole-dipole forces, so choice C is another one that we want to pick. So the correct answer is D, 2 of these, London dispersion forces and dipole-dipole forces. It will have both involved. The dipole-dipole forces are stronger, so they're going to be more important for determining key properties like vapor pressure and boiling point and viscosity, all that stuff that we learned about, but it has both of them, London dispersion and dipole-dipole would both contribute. Yep. AX4E? Are you in my section? No, yes, because this is how I covered VSEPR. Not everybody covers it this way, but basically it's the notation that allows us to classify the three-dimensional structure of this. So it's 4 atoms bonded to the central atom and 1 lone pair, so that gives us AX4E. And that tells us that it's a seesaw geometry, if we wanted to think about the geometry, and seesaw geometry will always give you a polar molecule. Anything else? Yeah. Can I explain to you what? Yeah, so intermolecular forces is sort of what this question is asking about. That's going to be weak forces of attraction. It's either going to be dispersion forces, dipole-dipole forces, or hydrogen bonds. Relatively weak forces that involve interactions between 2 molecules or between a collection of molecules with each other. Intramolecular forces with an A, INTRA, those are bonds. Those are things like covalent bonds, ionic bonds. Those are the forces, they're very strong forces that hold atoms together. So when you have SF4, each of these covalent bonds between sulfur and fluorine is an intramolecular force that's keeping the sulfur and the fluorine attached to each other. When we're talking about intermolecular forces, we're talking about 2 of these SF4 molecules and how they interact with each other. and because it's a polar molecule, they'll interact both through London dispersion and dipole-dipole forces. So that's kind of the difference between those two. They're two separate concepts, even though they have similar names associated with them. But intermolecular forces are not really chemical bonds; they're just weak electrostatic forces that exist between molecules that are in close contact with each other. All right, other questions? All right, on to the next one, number 18. All right, and then what we also have to deal with in Chapter 9 is certain key properties that relate to the intermolecular forces. So the reason these intermolecular forces are important is that especially for liquids and solids, they determine some of the key properties. They're correlated with the key properties. So we want to know which of the following does not increase with the strength of an intermolecular force. All right, so again, the intermolecular forces, the dispersion forces are the weakest, dipole-dipole forces in the middle, hydrogen bonds are the strongest, and even within those three categories, different substances have different strengths for intermolecular forces. And which of these properties then is going to not increase with the strength of the intermolecular force? So we have two phase change temperatures, melting point and boiling point. And remember that for both melting and boiling, we're taking a solid substance and we're breaking intermolecular forces to make it into a liquid. And then for boiling, we're taking a liquid which has intermolecular forces and we're completely breaking those to liberate the molecules into the gas phase. So the stronger the intermolecular forces, the more heat you have to put in to get those forces disrupted and to undergo phase transitions from solid to liquid or liquid to gas. So both of these increase with increasing intermolecular force. So the stronger the intermolecular forces, the higher the melting point, the higher the boiling point. So both of those will increase. If we go to the next one, which is viscosity, this is, again, the definition of viscosity is resistance to flow. It's basically how thick a liquid is when you try to pour it. And viscosity is one that also increases with intermolecular forces. So compounds with strong intermolecular forces tend to be very thick liquids. Compounds with weak intermolecular forces tend to be very thin, runny liquids. So this one also increases with increasing IMFs. Surface tension, this is the resistance of a liquid to change its surface area. So it basically gives the upper surface of a liquid, which has some amount of rigidity associated with it because it doesn't want to spread out any further because of the intermolecular forces holding it together. So this also will increase with intermolecular forces. So all four of these deal with intermolecular forces. Melting and boiling involves breaking intermolecular forces to change the phase of the substance. Viscosity, again, deals with how strongly the molecules are attracted to each other and their ability to flow and move over each other as you try to pour them out as a bulk liquid. And then surface tension, again, is the intermolecular forces of the liquid pulling down on the surface and giving that surface a little bit of rigidity. So all four of those do correlate, but then if we talk about ideal gas behavior, this is the one that does not increase with strength of intermolecular forces, because the ideal gas law assumes that there are no intermolecular forces. So if we do have intermolecular forces and if they become stronger and stronger, the gas is going to behave less and less ideal. So when we talk about deviations from the ideal gas law, deviations from PV equals nRT, those are going to be the most severe in gases that have strong intermolecular forces. So this is the answer we want to pick because the ideal gas behavior is going to decrease. It's going to become less ideal in the situations when you have intermolecular forces. Okay? Anything on this one that we want to rehash? All right, on to number 19 then. Number 19, so this one deals with the sort of lattice structures, crystal structures that we talked about. On this exam, you only have to deal with either this type of question, which is sort of how do we count the atoms in a unit cell like we're doing here, or the structure of metals by themselves, just one type of atom in the unit cell. We covered also more recently structures of ionic compounds. That's not going to be covered until the final exam, so you won't have to be tested on that just yet. But we do have to deal with structures of metals as well as some of the basic concepts and definitions associated with these cubic crystal structures primarily. So in this case, we have a partially filled cubic unit cell that has 4 corner atoms, 2 face atoms, and 4 edge atoms. How many total atoms are there in this partially filled cell? So what we have in this case is, again, a cubic cell. So our unit cell can be drawn as approximately as a cube. All right, so that's our unit cell, and what we're showing you here is that we have 4 corner atoms. So in blue, I'm going to show we have 4 atoms in the corner. We have 2 face atoms. Those are going to be right in the middle of a face. And we have 4 atoms on the edge, which we'll do in the third color here, green. So we have 4 on the edge. So 4, 2, and 4, these are the edge positions. So again, in these cubic unit cells, we can put atoms in different locations on the cell. We can either put them right in the corner, we can put them on the center of one of the square faces, or we can put them along the edge. The last type would be in the very center of the cube, which we sometimes have as well, but not in this problem. So when we're counting them, then we have to think about, for each of these positions, how many other neighboring unit cells are they shared with. So if we want to count the number of atoms in net that we have, in this structure we have 4 corner positions filled, and each corner is shared with how many adjacent unit cells? It's going to be 8. So if we stack these all together, there's going to be 8 cubes that share one corner. So think about stacking blocks with each other. There's going to be 4 in one layer that are going to share that same corner where they all intersect, and then 4 above that also share the corner at the bottom of those 4 cells. So it's going to be each are going to be shared by 8. So we count each corner position as 1/8 of an atom for that unit cell. So that's going to be our corner positions, 4 times an eighth in this case. We have 2 atoms on the faces of the unit cell, and how many unit cells are going to share a face of a cube? 2, because when we stack cubes next to each other, we put the 2 faces right next to each other like this, face to face, and that's going to have then 2 unit cells that share each face. So there's going to be, we're counting as a half for each face position. And then we have 4 atoms on the edges in this partially filled structure, and how many are edge positions shared with? 4. So as you arrange the unit cells next to each other, you'll have 4 that all intersect at a given edge of the unit cell. All right? You see these are the edges. And so in that, this partially filled unit cell has 2.5 atoms in it. None of the stable, metallic structures that we talked about would have this partially filled arrangement. But again, this is just a hypothetical situation where we're partially filling the unit cell. Because in total, we could put up to 8 atoms on the corner because there's 8 corner positions. We could put up to 6 atoms on the faces because there's 6 faces, and up to 12 on the edges. But in this partially filled one, we end up with this number here, 2.5 atoms in total. All right? Which, of course, you can't have a half an atom in real life, but that would be how we would count it in the context of one unit cell for this particular substance. All right, any questions? All right, last one here. We have also some questions on this exam that deal with classifications of substances, especially now solid substances like we've been talking about mostly in Chapter 9. So we have an element that's found to be a good conductor of electricity, has a high boiling point, and is malleable. Which of the following could be that element? So basically in this type of question where we're classifying an element based on its properties, we want to think about, is it a metal or a nonmetal? Because metals and nonmetals have very different properties from each other when they're in the solid phase. And for nonmetals, I'm going to say most have these properties because there are some exceptions. So in terms of their electroconductivity, metals tend to be conductors, and most nonmetals are insulators. So they're distinguishable based on that in most cases. Some nonmetals are semiconductors, or at least the metalloids like silicon, and also we learned about graphite in class, which is one form of carbon that does conduct electricity. So there are exceptions, but most nonmetals are insulators. If you were to take iodine, I2, or if you were to take ice, water as a solid, all those would be insulators. In terms of their what we call their mechanical properties, which is either how malleable or how brittle they are, whether they can be bent or whether they break when you try to deform them. Metals tend to be malleable, meaning that we can deform the shape, we can bend them, we can stretch them a little bit, change their shape, especially in a sort of a bending sense, whereas most nonmetals are brittle. All right, some nonmetals are very hard, like diamond, but they're brittle, meaning that if we try to change the shape of them, they're going to tend to just crumble, not be able to easily be bent or reformed into a new shape. All right, so that's true for just about every nonmetal. In terms of boiling points, most metals have high boiling points. All right, because you have these delocalized metallic bonds that are holding all the atoms together. And if you want to separate all the atoms from each other into the gas phase, you have to break all of those metal-metal metallic bonding interactions, which are relatively strong. Most nonmetals have low boiling points. The exceptions being the atomic solids like carbon, graphite and diamond, as well as some of those semiconductor structures. But most nonmetal substances, whether they be, most elements especially like the halogens, Cl2, Br2, I2, all those, they have relatively low melting points because in the solid phase, those molecules are only held together by London dispersion forces, which are very weak. All right, so in classifying the elements, we see that this one here is a good conductor, a high boiling point, and malleable. The three of those together tells us that it's a metal, and so we just have to figure out which of these 5 elements is a metal. We have sulfur, phosphorus, neon, gold, and iodine. What I should have told you in this problem is that the symbol for gold is AU, symbol for iodine is I, because those are beyond atomic number 36. You don't have to memorize them. But we have, I already forget which ones they were. So it's sulfur, phosphorus, neon, gold, iodine. Okay. So sulfur is there. That's clearly a nonmetal. Phosphorus, nonmetal. Neon, nonmetal. Iodine, nonmetal. Gold, which is right here, is in the transition metal series, so it is a metal. So it would be expected to have all those properties. So the only metallic element in these answer choices is gold, so that would be the one that we would expect to have these properties. So again, there will be some questions about classifying solids. I gave you some more details about that at the end of class, at the beginning of class on for this previous Wednesday. This question just really deals with the gross classification of metal versus non-metal and how that affects the properties. All right, thank you guys all for coming today. I will post this on YouTube as well as the answers will be posted in Blackboard as a PDF. If you have any additional questions, I can stay after for a little bit, or I can answer those anytime before you take your exam.